Go back to where we were. Mr. Yee, okay, just to summarize then, just a final movement to it. All right. And so we were talking, I'll just review what we said before. We had the action as an integral from T1 to T2 of a Lagrangian, which was a function of various Q's, Q dots, and possibly time, integrated over time. The change in the Lagrangian due to the first order change in the Lagrangian due to a change in the trajectory of the a change in the process, which is to say a change in the QIs of T, is an integral from T1 to T2 of, if I'm going to be completely explicit, it's the sum over I, partial L, partial Q sub I, minus d by dt, partial L, partial Q I dot, and this was multiplied by the change in QI, and this whole thing is integrated over time. And then, due to the integrations by parts, there's a boundary term, which is sum over I, the change in QI, and partial L, partial QI dot, evaluated at T2 and T1. Okay, so that's how the action goes. And so the principle of least action is that if we don't vary the endpoints, so we have a path that goes like that, and then another path that also goes there, so that this term is explicitly zero because the delta Q's are zero at T1 and T2, then if the first order change in the action is zero, that can only happen since the delta QIs are completely arbitrary but small. This is then zero is partial L, partial QI minus d by dt of partial L, partial QI dot. And so these are called Lagrange's equations. And if the Lagrangian is time independent, then so if partial L partial T is zero, then something is conserved, and I'm going to just call it E as a sum on I, partial L partial QI dot times QI dot minus L. This is conserved in time, and if you can do a Legendre transformation and re-express the QI dots in terms of the Q's and the P's, then this is the Hamiltonian of Q and P, where P is defined as partial L partial QI dot. Now, in virtually all the systems that one considers in physics, you can, after you define PI as the partial Lagrangian with respect to QI dot, you can then invert that and get QI dot expressed as a function of P and Q. and you can construct a Hamiltonian. Whether or not you can do that, though, this thing is conserved because the Lagrangian is time independent. It doesn't have any explicit time dependence. And the reason for that is that E dot would be ddt of this, or if you want, partial L, partial Qi, well, all right, ddt of that, times Qi dot, plus partial L, partial Qi dot, Qi double dot, then minus L dot, and minus L dot would be partial L, partial Qi dot, minus partial L, partial Qi dot, Qi double dot, and then there would be this term, partial L, partial T. But of course, when I say that the energy is conserved if partial L partial T is zero, partial L partial T is zero, I mean that Lagrange's equations guarantee that E is conserved. And so what happens here is that by Lagrange's equations, this thing is equal to that, and so these two terms cancel. And moreover, this term and that term, well, they're identically the same. And all we're left with is this. So if this is zero, the energy doesn't change. And this is true of any theory, including in any theory in which Lagrange is independent, doesn't have any explicit dependence on time, which is another way of looking at that is the theory doesn't have a past due date or a use-by date in the action, okay, in Lagrangian. In particular, in general relativity, you also don't have any use-by date. And so you can define an energy in GR and it's conserved. And that's related to inflation. What happens in inflation is the tiny, due to a quantum fluctuation or some initial instability, there's a tiny region that has very high potential energy. Then the equations of GR require that to expand like crazy. And it expands. You then have a huge region of high potential energy. That huge region then goes from, that potential energy is then converted into radiation. That's the Big Bang, and the universe results from it. You might say, well, how is energy conserved in this? It looks like what the Republicans would characterize as a democratic form of economics. Anyway, and the reason is that when this fluctuation, when this small region of high potential energy inflates really rapidly, negative potential energy is created, negative gravitational potential energy in equal amounts is created, and so you have conservation of energy. Okay. One thing to notice here is that the change in the action so here when we were deriving Lagrange's equations, what we said was that the delta Q's were zero at the boundaries at T1 and T2. But if we want, if we instead have these non-zero at T1 and T2, then what we see is that the partial of L, partial of the action with respect to, say, how did I write it? Qi is just equal to Pi. So in other words, consider the time T2, and the change in the action if you change the endpoint by a little bit, then ds divided by dqi is just partial L partial qi dot. That's pi. Okay. Now, there's this business of symmetry, which I went through very briefly in the oh, by the way, let me just, I'm going to make this very brief, namely, you can also look at ds dt, in as much as s is the integral of L. ds dt is clearly L. And on the other hand, ds dt is partial s partial t plus partial s partial qi dot, but this is then partial s partial t. This is the pi. By this equation, that's pi. And so now what you see is that the partial s partial t is equal to L minus pi qi dot, and that's what we call minus the Hamiltonian, assuming we can invert the equations. And so this tells us then explicitly if well, this just gives us a relation that's like one of these relations again. Okay, now symmetry. Symmetry, or one kind of symmetry, is that delta L is 0 for a certain transformation. And what would delta L be? Well, it would be a sum on I, partial L, partial Qi, the change in Qi, plus partial L, partial Qi dot, change in Qi dot. Or if we just assume, so this being equal to 0 means that you have a symmetry of some sort. And if we write that in terms of the p's, then it's 0 is partial L partial Qi, change in Qi, plus pi change in Qi dot. So the symmetry is, if that's 0, you have some kind of a symmetry. And this symmetry, though, leads to a conservation law. And the conservation law is that a quantity, and let's see, what should I call? I guess I'll call it C for conserved quantity. The conserved quantity is a sum on I. Let me use the pi notation. Pi change in Qi. So this is the change in Qi that under which delta L is 0. So another way of writing it is partial L partial Qi dot change in Qi. Okay, so the point is that C is conserved if you have a symmetry. And in order to see that, well, C dot, what would C dot be? Well, it would be, let's use this form of it. It would be ddt of partial L partial Qi dot times the change in Qi plus partial L partial Qi dot times delta Qi dot. On the other hand, by Lagrange's equations, by the way, the symmetry implies that if you have Lagrange's equation, then this thing is conserved. And so Lagrange's equations tell you that this thing is equal to partial L partial Qi delta Qi plus partial L partial Qi dot delta Qi dot. But this is 0 by the symmetry. This is exactly the symmetry condition. So the symmetry condition gives you conservation of a quantity. The quantity is always of the form partial L partial Qi dot delta Qi, or equivalently Pi delta Qi. This isn't in the first edition of the book. This is new stuff that I'm adding. Yes?
So Q is an action and P is momentum? Is that correct?
All right, hold on. Oh, great catch. Wow. Say it again.
So Q is an action and P is momentum, is that correct?
Q is an action?
Is that?
No. Q are the coordinates.
Okay.
Okay. In fact, here, these are the coordinates Q at, say, time t1. Let me get my nice chalk. That's Q at time t1. And these Q's, it could be, 3 Q's, like the position of a particle at time t. And this is Q of t2. So the idea of Lagrange depends upon the coordinates and the velocities, and possibly the time, if it's non-autonomous. I don't know why we use this term, autonomous. Autonomous is just a fancy word for time independent. Time independent is clear and autonomous is obscure. Okay, so basically, classical physics is basically a larger fraction of classical physics is the statement that the action is an integral of some Lagrangian, that the classical equations of motion follow from the requirement that the action be stationary. If the Lagrange's equations here are satisfied, the energy, or equivalently the Hamiltonian, is conserved in time. The momenta, by definition, are the partial of the Lagrangian with respect to the velocities. And a symmetry is when the Lagrangian doesn't change when you make some change in the process. And the Q is at a particular point in time, say. And that then implies that a certain quantity C is conserved. Yes?
I was going to ask, so saying that this delta L is 0, this is in...
Yeah, that means that L doesn't change when you do this.
Yeah, no, okay, but what I'm asking, so this is dependent on the coordinates that you pick. Like, in order to find the symmetry, do you have to pick the right, set of generalized coordinates such that you can say that delta L is 0? Like, is this true in every coordinate?
That's worth another piece of candy. Yes.
Okay.
If you use screwy coordinates, it might be hard to find the symmetry. But of course, if there's a symmetry, it's there.
Yeah. Okay.
All right.
So the idea is to just find the correct set of coordinates such that delta L goes to 0, and then from there you can find out what this conserved quantity is.
Right, but delta L is 0 in other words, you can re-express whatever the thing is that you do, you can re-express in any coordinate system, and in that coordinate system, delta L will be 0. So no matter what coordinates you use, the symmetry is there and you can find C. But if you use an intelligent set of coordinates, then the symmetry is more apparent, and this expression for the conserved quantity is simpler. Let me give the famous example, two famous examples of this. So, Well, the first example was over here. We said that the Lagrangian doesn't change when you change the time. That led to conservation of energy. All right, suppose the Lagrangian doesn't change when you change all the Q's. Delta Qi. Well, all right, here, let me follow your advice and go from arbitrary generalized coordinates to ones that are useful for momentum and angular momentum. Then what we'll have is R, I, and that would be xi, yi, zi. So those would be the coordinates that we use, rectangular coordinates, say. And then this, the change that we're talking about is delta Ri would be just simply ABC. In other words, the displacement of every coordinate, every position, every point of the location of every particle you move by the same amount. Then what's the thing that's conserved? Well, the conserved quantity is the sum of pi delta qi. So this would be the sum of Ri dot ABC, where Ri are the positions of all the particles. And I'm sorry, pi, what am I doing? This is pi, okay. And so what is that? Since ABC are just arbitrary constant vectors, we can say that the thing that's conserved really is the sum of all the momenta of all the particles. So that's conservation of momentum. So conservation of momentum follows from delta L equals 0 when the delta of the coordinates is just displacement by a 3-vector, the same 3-vector for every coordinate, every set of 3 coordinates. And as you point out, this is more natural it's easier to write down and think about in rectangular coordinates. Now another, staying with these R's, let's suppose instead that delta Ri, the position of the ith particle, suppose that changes by theta cross Ri, where theta is a 3-vector. This is an angle. The magnitude of the 3-vector angle is the number of radians in the rotation. And if all the coordinates change by this amount, then what you're doing is you're rotating the whole system about the origin and about a vector. So you have some vector theta like that. You're rotating everybody around theta. Okay, around theta. And in that case, what is conserved? The thing that's conserved now, and so we would call this thing P, the sum of all the momentum. This thing would be called, in this case, angular momentum, because it would be a sum of pi delta qi. So this would be a sum pi, now I'm using that as a 3-vector, dotted into theta cross Ri. And you can rewrite this as theta dot sum on I Ri cross pi. So the thing that's conserved due to the symmetry of symmetry under rotations is angular momentum. Yes.
I have another question. So you don't have to give me.
You really want to stock up your
No, I have
TV
too
store.
much
I know what you're doing.
No, so okay, so in an example, like if you consider the Lagrangian like for a free particle, I can see why dl dqi would go away. That would vanish. But dl qi dot, that would not vanish. But would it vanish because
Well, yeah, there's no change in qi dot if you just do a translation or a rotation.
There's no change in qi dot O.
In other words, d by dt,
I suppose that makes sense.
well, certainly d by dt of Ri would be 0. Delta
Yeah.
Ri would be 0 because it's just ABC.
Mm-hmm.
And
But would your delta Ri have to do?
And then over here-
on time in order
over
to-
here, delta Ri is just theta cross Ri.
Mhm.
So that's time independent.
Sure. Sure. So in order for the term that's dl dqi dot delta qi dot to not vanish, your delta q would have to be like time.
Well, it's not that these vanish independently, it's that the sum of
Oh,
the two
sure.
vanish.
Okay. Yeah. Sure. Sure. But I'm just saying. Your delta qi would need to depend on time. Would it have to have like an explicit time dependence?
I'm sorry, say that one more time.
Would your delta q sub I have to have an explicit time dependence in order for it not, since you're differentiating it, would you need some explicit time dependence in there?
Oh, gosh. I'm not sure what you're getting. Why don't we talk after class?
Okay.
Because there are other subjects we have to get to.
Sure.
You know, have an office down the hall there?
Yeah, I know.
All right. All right, let's go to something that's very important in physics, and it's extremely common. So I'll just follow my notes rather than try to improve things. So suppose we have a standard Lagrangian. Some m sub I over 2 xi dot squared minus u of x. So this x is all of the x's, so 3n coordinate set. And another way of thinking of this is some mi r vector I dot squared over 2 minus u of x. Okay, so this is a sort of generic Lagrangian in mechanics. And what we can do is we can scale out the mi to make this thing simpler. We can say qi is square root of mi over m xi, or if you want to use 3-vector notation, ri. And then this thing becomes m over 2 sum qi dot squared minus v to q. So I'm changing from x to q, and when we do that, we're effectively giving all the coordinates the same mass. Okay. The Hamiltonian is then a sum pi squared over 2m plus v of q. And now, since the Lagrangian doesn't have explicit time dependence, the energy is conserved, and what you typically, if you have a reasonable physical system, the potential is bounded below somewhere. It's bounded below and has a minimum somewhere. If it's not bounded below, then the system can sometimes find its way. Quantum mechanically can always find its way and leak down a slope that goes to minus infinity. So let's just assume that there's a minimum somewhere, and then what happens typically, especially if we consider the system more generally in a thermal bath, so that the thing can fluctuate and jump over little hills and eventually find the absolute minimum. So what happens is if the absolute minimum is at q equal to q0, so this is the minimum of the energy, minimum of the potential is actually what we're talking about. Then what happens is, I'm puzzled as to why I went to, So we can expand L around the minimum, and it is roughly m over 2 sum Ri dot squared. But that now since this is a minimum, the derivatives of V, all the derivatives, all these first derivatives vanish. And so this is equal to minus a half. And now I'm using I guess I shouldn't use R for too many different. Oh, okay. So
shouldn't that be in that one? Shouldn't that be the Q's? Because the Q's are the one that use Cahill, so you can pull out the mass. Otherwise, you have to sum over the mass.
right. But yeah, you're right. I'm using two different notations. Forget that I called this R.
Okay.
Call it R twiddle or something. And I'll give you a candy in a minute. These RIs are QI minus QI0. So these are the relative coordinates relative to the absolute minimum of the potential. Then these things are a sum on J and K, Rj, Rk, partial to V at the minimum, partial Qk, partial Qk. Okay, so we can write it this way. And another way of writing this is m over 2, a sum Ri dot squared minus a half. And we can think of this as some Rj, Rk, B double prime Jk. That's perhaps a better way of writing it. This matrix of partial derivatives is obviously symmetric because partial 2v, partial qj, partial qk is the same as partial qk, partial qj. So that's symmetric. We can diagonalize it by an orthogonal transformation. So we can write it this way. That D for diagonal like that. And so what we eventually get is that L is then a half sum I equals 1 to 3n m. Okay, we make this transformation. I'm changing variables again. S is equal to OR. So O is a 3n by 3n orthogonal matrix. R are these original 3n coordinates. The S's are the image of the R's under the orthogonal transformation. So then what we have here is SI dot squared minus V double prime diagonal. So these are just entries on the diagonal. The ith entry SI squared. So these are harmonic oscillators. These are also called the normal modes. So what emerges in this is that for an extraordinarily general class of mechanical problems, as long as the potential is bounded below, the system will typically find itself near the absolute minimum. It'll then be vibrating around the absolute minimum in a motion that is a sum of these various normal modes. The normal modes we can write as SI of t is an arbitrary coefficient cosine square root of V double prime, the diagonal form, the ith entry over m times t plus some bi sine square root b double prime di over m t. So, under enormously general conditions, what you have are called small oscillations about the absolute minimum. Okay, well, let's see, I owe you candy. Hold on. Well,
Have a candy too.
huh?
Have a candy too.
I suppose that is a question. All right, now we're going to be talking about something that is a little more technical, but the strain shouldn't require you to use any opioids. In fact, there was a study that I saw recently, and the study said that if you gave, in the study they gave people with fractures and other very painful injuries acetaminophen, which is Tylenol, and ibuprofen, which is Advil. Gave some of them that, they gave others the opioids. Asked them how much pain they had after 30 minutes or something for the system, for the bodies to equilibrate. No difference. So in other words, people with ordinary injuries, I'm not talking terminally ill cancer patients, I'm just talking run-of-the-mill problems, backaches, fractures, broken bones, street fights, whatever. Advil, or let's just say acetaminophen plus ibuprofen costs 10 to 15 cents, non-addictive, just as effective as opioids, $5, $10, $20 a pill, and addictive. And so we see that the pharmaceutical industry, which has been pushing opioids, is truly criminal. Not quite as bad as the tobacco industry, but really bad. And incidentally, they rented the Congress for a few days and had a law passed so that whenever you go to a clinic, the nurse won't just take your blood pressure and weigh you and so forth. The nurse will say, "Are you in pain?" That's a required question by federal law put in by the opioid industry, so that people will vocalize their pain, and that will lead to more opioid prescriptions, which have been multi-billion-dollar profits for illegitimate pharmaceutical companies. Okay, sorry for the tirade, I just couldn't help it. And maybe if you run into anybody who is in pain, Tylenol plus ibuprofen is the way to go. Cost pennies. Okay, singular points. Okay, so we have a differential equation. And let's just write the differential equation as y double prime plus p of x y prime plus q of x y equals 0. All right. Now, if p and q finite at, let us say, x0 implies x0 regular form. These are just definitions. On the other hand, if x minus x0, p of x, and x minus x0 squared, q of x, remain finite as x goes to x0, then x0 is a regular singular point. Well, singular I messed up, but anyway. Okay, so P and Q finite, regular point. P and Q infinite at x0, but these ones finite as x goes to x0. X0 is a regular singular point. These are the ones you learn to love. The alternative is an essential, an irregular, otherwise, so I'll just write else. It's called an irregular singular point, and that's equivalent to an essential singularity. I don't think this is essential singularity in the same sense as in complex variable theory, but it might. Okay, for the point at infinity, people do two things. Some people just change variables and let z equal to 1 over x, and then they repeat the same thing in terms of z. A simple way, I think, of describing it is, so suppose P and Q, if P and Q are finite as absolute value of x goes to infinity, then the point at infinity, and the point, people use this language, the point at infinity, to include both plus infinity and minus infinity. So this is then regular. It's an infinity regular point. If 2x minus x squared p of x and x to the 4th q of x are finite as x, absolute value of x to infinity, then this is a regular singular point. So, well, let's see, if those are finite, then infinity is a regular point. If these two guys are finite as x goes to infinity, then infinity is a regular singular point. And if, on the other hand, 2 minus x p of x and x squared q of x goes to infinity, okay, wait a minute, I've said this wrong, sorry. It's if 2x minus x squared p and x to the 4th q are finite, then, oh, that's right, regular singular, I did say it correctly. If, no, I said it wrong. Regular point, not regular singular, sorry. So infinity is a regular point. So forget what you see. If 2x minus x squared p and x to the 4th q remain finite as x goes to infinity, then infinity is a regular point. If these remain finite as x goes to infinity, then infinity is regular singular point. And otherwise, if it's worse than that, then it's an irregular singular point, or an essential singularity. All right. In the book, I describe it in terms of z, and I thought this afternoon it was simpler in terms of x, and so I wrote down the conditions. Then I screwed up my delivery. Okay, the next step is Frobenius' solution. So Frobenius figured out ways of solving differential equations systematically, and these are important to know about. So the first thing we're going to do is we're going to change notation from capital P and capital Q to lower p and lower p. In particular, we're going to say little p is going to be x big P, and little q is going to be x squared big Q. So then we're going to rewrite the equation x as x squared y double prime plus x p of x y prime plus q of x y equals 0. And of course y is a function of x. So this is our equation, and we're going to use Frobenius' method to solve it. And we're going to assume, for the moment, let's assume that p and q are polynomials in x. And to make the notation simple, I'm going to say that p of 0 and q of 0 are finite. And so consequently, x equals 0 is a regular point or a regular singular point. So x equals 0 is regular or regular singular point. Okay. Now, what we're going to do is we're going to try to find solutions about x equals 0. We could choose any other point, x0, but obviously that would make it a more complicated equation. It doesn't introduce anything new. So what we do is we expand it this way. Y of x is x to the r times the sum an x to the n equals 0 to infinity. And what is r? R is chosen so that a0 is not equal to 0. So in other words, equivalently, r is lowest power of x in our solution y. All right, if we differentiate this, we obviously get y prime of x is a sum r plus n an x to the r plus n minus 1, and y double prime of x is sum r plus n minus 1 an x to the r plus n minus 2, and these sums both go from 0 to infinity. Okay, and so we've got these three expressions for y prime, and y double prime. Now, what you do is you take these three equations and you shove them into this equation, a differential equation. And then what you get is a rather complicated looking thing. It's complicated though because we're doing this in such generality. In any particular case, it's simpler in principle. Okay, a sum n equals 0 to infinity n plus r minus 1 plus n plus r p of x plus q of x a sub n x to the n plus r. Okay, so this is what we get, and what I've done here is in this case and in that case I've changed the I've changed n plus 1, I forget. But anyway, this is what one gets when one does the substitution. Now, if this is to be a solution of the differential equation, then every power of x in this thing has to, the coefficient of every power of x has to vanish. The lowest power of x is when n equals 0, you get a0 here, and notice a0 is non-zero, that's by construction. That's this choice. That's what determined R. And moreover, if n is 0, we have various powers of p, x, and p and q. But if we want the lowest power of x, it's just p0 and q0 here. So what this, so the condition that the lowest power, all power, the coefficient of every power of x has to vary. But in particular, for the lowest power of x, this condition amounts to r times r minus 1 plus p of 0 plus q of 0 equals 0. This is a quadratic equation, and the solutions are, or the roots are, 1 minus p plus or minus the square root of p minus 1 squared minus 4q over 2. These roots are called R1 and R2. This is called the indicial equation. You see, so far, we haven't really determined what R is. We're determining what R is from this equation here. So, the next thing is we set P, this again is the general solution. This is for the general case. This is from j equals 0 to, we said polynomial, so I'll just say pj, xj, and q of x is a sum qj, xj, both of them j equals 0 up to some finite power. And I'm going to set, sorry, this is p of 0, which I'm going to call p. I'm just going to write p0 is p of 0, q0 is q of 0. Okay, well, the requirement that the coefficient of every power of x vanish implies a recursion relation. And these recursion relations are ones that you've no doubt seen some of these in the past. I'm going to write down the general form, and it's 1 over r plus k r plus k minus 1 plus p0 plus q0 times the sum j equals 0 k minus 1 of j plus r p sub k minus j q sub k minus j aj. All right, so that's god awful looking. This k is the index on A. But basically this tells you, because if you wrote this as a computer program, you know, the computer wouldn't mind at all. It's just people who kind of object to things that are this complicated. But this tells you that AK is given in terms of lowered coefficients. So the thing is soluble. You know what A0 is. that gives you, let us say, A1. And then, once you have A0 and A1, you get A2 and so forth. That's generally how one proceeds. So this leads to a solution, and here, it's actually two solutions for R equal to R1, and then for R equal to R2. So you use both solutions. These are called the roots. They're just the roots of the quadratic equation here. This is called the indicial equation.
How do we know what A0 is?
Yeah.
How do we know what A0 is? Ah, good question. Well, this is a linear equation, and so since everything's going to be proportional to A0, doesn't matter what A0 is, right? In other words, you could, if you want, take A0 to 1, I guess, and then you'd have a solution. In fact, that might make all this a little bit, the notation a little bit simpler. In other words, the overall, if y is a solution, constant times y is also a solution, because it's a linear equation. I owe you a candy. Hold on. So, as I was saying, this is a little bit more technical, causes some sort of brain pain, Tylenol, and ibuprofen. All right. Okay, now the thing is that in most cases, most important cases, you're dealing with relatively simple differential equations, in which case P and Q are quite simple. And one example is y double prime plus omega squared y equals 0. Well, you know what the solutions of that are. They're just sine of omega x and cosine of omega x. This is the case where P of x is identically 0, and where Q of x is equal to omega squared x squared. So I'll let you read the rest of the example. What happens is you go through this and you find sine and cosine as the two solutions. Maybe I should add do you want me to go through it in detail, or can you just read it?
We can read it.
All right. Next one, more interesting, is Legendre's equation, which is sometimes written as 1 minus x squared y double prime minus 2xy prime plus lambda y to the... Yeah, this one is much more interesting. If we write this in the standard form, we have P of x as minus 2x squared over 1 minus x squared, and Q of x as x squared lambda over 1 minus x squared. Okay, so what you can see is that x equal to plus or minus 1 are singular points. However, they're regular singular points. That's funny, I didn't mention that. Okay, well, what does the recursion relation look like? The analog of that is a sum n equals 0 to infinity n plus r minus 1, 1 minus x squared, x to the n plus r minus 2. Actually, what I'm doing here Okay, first of all, these are not polynomials. So using straight Frobenius isn't the simplest way to go about it. Instead, the simplest thing is to just substitute these two things into this differential equation and I guess multiply through by 1 minus x squared, and then you wind up with Legendre's form. So that's the standard form. In other words, to get the p of x and q of x, you divide by 1 minus x squared. All right. In any event, what you find here is minus 2 n plus r, this is the recursion relation, x to the n plus r plus lambda x to the n plus r. an equals 0. This is the equation that's equivalent to this equation. It's not yet the recursion relation. The recursion relation, after a little bit of manipulation, is aj plus 2 is equal to j plus 1 minus lambda over j plus 2 j plus 1 times aj. Okay, now this is a lot nicer than the previous ones. But there's something very interesting about this. As you let j go to infinity, what does this become? This becomes a j plus 2 is essentially a j, because as j goes to infinity, this is j squared over j squared, which is 1. But then the solution that you'd get would diverge. So it wouldn't be a square integrable, wouldn't be a nice solution. So in order to have a nice solution, in other words, in order for the power series to converge, something special has to happen. Namely, lambda has to be such that for some j, this is 0. Once that's 0, all future coefficients vanish. Okay. So what this says is that lambda is equal to j plus 1. And that tells us that the solution then, which is x to the r some an xn, that sum doesn't go to infinity, it stops at j, and these things are called the Legendre polynomials. Okay. All right, now, I know a physicist who has been a professor at one of the universities in Arizona, whose name is Fuch, and he's very careful how he pronounces his last name. Anyhow, whether he's related to this Fuchs, I don't know. But Fuchs proved a theorem, and the theorem is that if you apply Frobenius' method, which I've just outlined, to a linear second order, so linear second order homogeneous ordinary differential equation, and you expand about regular point or regular singular point, then you always get one power series solution. And he was able to characterize them. If the two roots are the same, R1 equals R2, you get only one solution. The second characterization, if if R1 minus R2 is not an integer, or so let us say, not in n or z, the integers. If R1 minus R2 is not an integer, it's different by a non-integer, you get two solutions. And the third case is if R1 minus R2 is an integer, so that's z, then bigger root, so bigger R gives a solution. So use the bigger R to find your solution, not the smaller one. Okay, so that's Fuchs's theorem, and are there any questions? Okay, we can turn the thing off if you want, but let me